So this will be the last chapter of the semester. There are 9 sections in chapter 4. Usually I only cover 4.1 through 4.7, so you should make sure that that's what I'm doing this semester. That's probably going to be the case. It's all on probability. It shouldn't be that hard of a section, but this is the chapter where the test scores are generally the lowest, and that might be because students have a lot of extra points built up and they kind of calculate what they need to get on this test to get an A. Maybe they don't put the same amount of effort in. Anyways, this section is on probability, and most of the chapter's on probability. It's actually on probability and counting, but probability is the big portion of this chapter. So probability is the chance something will happen. We could say the probability is how likely an event will happen. For instance, I could say the probability, if I could actually write this morning, the probability that it rains today, that's the chance that it's going to rain today, is, let me say, 25%, just because it's cloudy today. I haven't looked at the weather forecast to really know. So this would be an example. The event would be it raining today. The probability is a numerical chance that that happens, and here I wrote it as a percent. I could say something like this: the probability the Phoenix Suns win the NBA championship this year is, how about 1 in 1,000? So probabilities are just the chance that something will happen. That's something we usually call an event. The events that I've talked about here are the probability that it rains and the probability that the Suns win the NBA championship. Notice in the probability that it rains, I use a percent to define my probability, and in the NBA championship, I use a fraction. These are the two common ways that when we attach a number to the probability that an event will happen, usually we either use percents or we use fractions. Regardless if we're using percents or fractions, the lowest possible probability is 0. 0 is the lowest or smallest possible probability. If I said there's a 0% chance it's going to rain today, that means it just can't happen. It's guaranteed not to rain. So a 0% probability means that event can't happen. So a 0% probability that it's going to rain would mean it's impossible, and we can't have negative probabilities. You can't say there's a negative 10% chance it's going to rain. 0 would be the smallest probability, and 100, or 100%, I guess, really 0 and 0%, 100% is the largest possible probability. I just got done doing a trail run, and it's, I don't know, I think it's 40 degrees. My wrists are just, I broke my wrist when I was a kid, and it's not really working right now. Anyways, if there was a 100% chance it was going to rain today, then it would be 100% guaranteed, absolutely for certain it's going to rain today. You can't have a 150% chance it's going to rain. The smallest probability is 0. 0 means an event can't happen. The largest probability is 100, which means the event has to happen. Most probabilities are somewhere between 0 and 100%. So generically, there are 3 different kinds of probabilities, and the probabilities that I have been working with right now on this sheet are subjective probabilities. And a subjective probability is really just a guess. A subjective probability is just an educated guess, for instance. And I made educated guesses by looking at the clouds outside and knowing something about what the Suns team looks like this year when I made it these probabilities. They were subjective probabilities, and I may be wrong on both of them, But nevertheless, these are just my educated guess, and that's what a subjective probability is. It's just an educated, or just really it's just a guess based on whatever data that you have. If I asked another person these questions today, what's the probability that it's going to rain, or what's the probability the Suns are going to win the NBA championship, a different person might make a different guess. These are just really loose, not very accurate, not necessarily very accurate probabilities. The next kind of probability that we'll look at in this section are empirical probabilities. And empirical probabilities are probabilities that are experimentally determined. You don't need to write down these definitions at all. That would kind of not be what I'm hoping for. Eventually we'll learn how to use the concepts, but don't worry about the definitions. Okay, so empirical probability is probability which is experimentally determined. We gather numbers in some fashion, and we use the numbers that we gather to estimate probabilities. Of course, if you're using data to estimate probabilities, then your estimation is only good as the data collected. If you didn't use sound statistical methods to gather the data, then your probabilities might not be very accurate. In general, we form empirical probabilities by creating fractions, and we'll get to this in a little bit, but there's a formula for empirical probabilities that we'll go through in a little bit. It says the probability of some event happening, like the probability of the Suns winning the NBA championship, or the probability that it rains today, it can be formed by a fraction, and in the numerator it's going to look at all the data that's been collected for that particular event and find the number of times that event has occurred divided by the number of observations you took when you got the data. This is too abstract right now, so let me work through a couple of examples to help you understand empirical probability. Subjective probability is something that's kind of hard to test on because it's based on your guess or my guess or somebody's guess, and that's too loosely defined to test on. But empirical probability is not so loosely defined. So let me help you through the empirical probability a little bit with an example. So 100 GCC North students were asked what high school they attended. The results are given in the table below. So this is kind of a frequency distribution. If I added up all the student responses, of the 100 students, 26 went to Sandra Day, 20 to Mountain Ridge, 14 to Boulder Creek, 10 to Sunrise Mountain, and then 30 in some other high school that's not one of the common four that students at GCC North come from. Centennial, I went to Thunderbird, maybe Thunderbird, Greenway, Deer Valley, any other, Northwest Christian. So I lumped all the other students that weren't in the four most common feeder high schools to GCC North in a big other category. So this is the data. So when we're doing empirical probability, we gather data, and this is the data that I gathered. And now I'm going to use the data gathered to answer probability questions. Probability questions. And this is going to be empirical probability. Every one of the answers are the questions that I ask because I'm using data that's been collected. This is going to be an example of computing probabilities using empirical probabilities. So, first question. Find the empirical probability that a randomly selected GCC North student went to Mountain Ridge. So I only surveyed 100 GCC North students. Maybe there's 4,000 GCC North students this semester. So what's the probability that if I just go up to a GCC North student and ask them what high school that they went to, what's the probability that that student went to Mountain Ridge? Super easy to do this. To do empirical probabilities, you form a fraction. The numerator of the fraction has the number of, in this case, students that fit what I want them to fit. In this case, they went to Mountain Ridge. In my survey, 20 of the students, of the 100 students that were surveyed, went to Mountain Ridge. I'm trying to find the probability that a student went to Mountain Ridge. 20 is going to be my numerator. And for empirical probability, the denominator is the total number in the survey, the total number of observations. And there were 100 students surveyed or observed. That's going to be in the denominator. So we'll say 20 of the 100 students that were surveyed went to Mountain Ridge. So I'm going to use that to make a probability estimation. So if we randomly pick a student from GCC North, not necessarily one of these 100, what would I guess the probability that they went to Mountain Ridge? I'd say 20 and 100, and I could reduce that fraction to 1/5. Usually when we answer a probability question, we either give the answer as a percent or a reduced fraction. And I'm going to do the reduced fraction here. If I did 20 over 100, now I'm going to go math and enter twice to get that 1/5. But because my question said write my answer as a reduced fraction, I'd probably write 1 in 5, which means there's a 1 in 5 chance that if you walk up to a GCC North student and ask them what high school they went to, that they would say Mountain Ridge. Here's another part. Find the empirical probability that a randomly selected GCC North student did not go to Sunrise Mountain. Well, again, I'm going to form a fraction to do this probability. In the numerator, it's going to be the number of students that did not go to, I'm out of room right here, so I'm going to do SM for Sunrise Mountain and not Shadow Mountain, divided by the total number of students surveyed. So this is empirical probability. I'm using the data in my table, and when I try to answer a probability question, I'm going to create a fraction. The numerator of the fraction is going to have the number that have the desired characteristic, the number that did not go to Sunrise Mountain. For that numerator, I could add up this 26, this 20, this 14, and this 30. I get 90. If I was slick, instead of going 26 plus 20 plus 14 plus 30 and getting 90, I would have just taken the 100 students minus the 10 that went to Sunrise Mountain, and that would give me the 90 that didn't go to Sunrise Mountain. So my numerator is going to be 90. It's the number of students that did not go to Sunrise Mountain. The denominator is the number of students surveyed, which is 100. This is a fraction I can reduce pretty quickly by just lopping off the zeros. And the answer to the question, what's the empirical probability that a randomly selected GCC North student didn't go to Sunrise Mountain? The answer would be 9 in 10. Okay, the next question's a little bit harder, but hopefully not so hard. I think even if I didn't explain how to do this, you might be able to do it. So if 500 GCC North students were asked which high school they attended, how many would say they went to Sandra Day O'Connor? Well, what I'm going to do is first find the fraction of students that went to Sandra Day, and then I'm going to multiply it by 500. So to do this, I look at my table, and 26 of the 100 students went to Sandra Day. So I'm going to take the probability that a student goes to Sandra Day, which is 26 in 100, times the number of students that were asked, 500, and doing that multiplication will give me the number of students that would say they go to Sandra Day. So let me do this on my calculator. So I'm doing the probability that a single student goes to Sandra Day times the number of students asked. That's 26 in 100, which is a non-reduced fraction, times the 500. That will give me the 130 students that I would say of these 500 that went to Sandra Day, because 26% of all the students surveyed said they went to Sandra Day. If you take 26% times 500, you're going to get this 130. So good enough maybe to get into some homework questions. So here's a table. We're going to use this table to answer some homework, some probability questions. I'll do problem 1 with you. I'll skip problem 2, then I'll let you do problem 3. So in a given week, a veterinarian treated 40 dogs, 35 cats, 15 birds, 5 iguanas, 95 total animals. So, determine the empirical probability that the next animal she treats is a dog. Super simple to do. This doesn't say to write it as a reduced fraction, so I could give the answer as a percent, but I'm going to give it as a reduced fraction. I'm going to form a fraction. In the numerator, it's going to be the number of animals that have the desired characteristic, in this case, the number of dogs. And in the denominator, it's the number of animals that were treated that week. It's always the number with the characteristic divided by the total. In this case, it's 40 and 95. And if I write 40 and 95 on my calculator and hit math and enter twice, I get 8 over 19 for my answer. So for part A, I'm going to write 8 over 19. For part B, the probability the next animal she treats is a cat, it's going to be the number of cats treated during the week divided by the number of animals treated in the week. And I think that reduces to 7 and 19, but I'm afraid I'm messing up, so let me do 35 over 95, math, enter, enter, and I get 7 and 19. Lastly, what's the empirical probability that she treats an iguana? It's going to be 5 iguanas over the 95, and I believe that reduces to 1 in 19. And again, I should always be safe. Go 5 divided by 95, math, enter, enter, and it's 1 in 19. So I'm not going to do number 2. I'm not sure if you can do number 3 without me doing number 4. So I'll do number 4. It's worded a little bit differently, but then I'll flash back and let you do number 3. For what it's worth, the answers that I have written down for 3A is 3 and 25, and for 3B I have 1440. So if you can pause the video and do those without me doing problem 4, then do them and skip watching me do problem 4. So problem 4 is supposed to be similar but a little bit different than number 3. So a manufacturer tested 1,000 radios, 15 of them are defective. Determine the empirical probability that a radio is defective. It's going to be found by making a fraction. The denominator is going to be the total number of radios inspected. The numerator is going to be the number of them that were defective, so it's going to be 15 in 1,000. And again, I'm going to write all my answers until I'm asked to write something as a percent, as a reduced fraction. I get 3 in 200 for that. So the empirical probability that if we take another radio from this company that it's defective is 3 in 200. And then estimate the number of defective radios in a shipment of 5,000. 15 out of every 1,000, if I just multiply that by 5, I'd probably get the 75 that were defective. I could take, if I wanted to do it with math, I can take either of these fractions that are the probability that the radio is defective and multiply it by the number of radios. Both this computation, 15 over 1,000 times 5,000, and this computation, 3 over 200 times 5,000, will give the same answer, and they both will be the estimate of the number of defective radios. If I did 15 over 1,000 times 5,000, or if I did 3 over 200 times 5,000, they both will give me 75. My answer to part B is I'm going to just say 75, and maybe I'll attach the word radios to it, or defective radios, but radios seems fine. So let me flash back your number 3 and see if you could push through that. For part A, you're just going to make a fraction and reduce it. For part B, you can take the answer to part A and multiply it by 12,000. Let me do problem 5 with you and not do problem 6, just so we can have it done. And I'm going to write the answers down that I'm supposed to get for 11A. 5A, I'm supposed to get 11 over 25. And for part B of number 5, I think I get 13. So let me work on 5A down here real quickly. So John has taught 500 Math 142 students. 220 of his Math 142 students received a grade of an A. Determine the empirical probability that a student in John's Math 142 class receives an A. To do empirical probability, I form a fraction. In the denominator, it's going to be the bigger or the total quantity, in this case, the 500 Math 142 students. In the numerator, it's going to be the number of students that have the desired characteristic. In this case, the desired characteristic is receiving an A. and 220 of them received an A. So the fraction I'm going to form has the number of students that received an A divided by the number of students, and now I'm going to reduce this, 220 divided by 500, and math, enter, enter, and I get that 11 over 25. For part B, estimate the number of A's John will give in a class that has 30 students, and then round to the nearest whole number. To do this, I can take this fraction, or the reduced version of this fraction, and multiply it by the 30 students. I'll keep my number smaller by taking the 11 over 25 version of this, and I'll multiply that by the 30. And hopefully that comes out exactly to 13, but if it doesn't, I'm just going to reduce and round. So this comes out to 13.2, but I can't say in a class of 30, John's going to give 13.2 A's. This says round to the nearest whole number, and the nearest whole number is 13. It might be nice if I might say students will get an A. So all of these are empirical probability questions. Tells me I'm doing empirical probability, but I'm using data that's been generated to answer probability questions, and that's what empirical probability is. Why don't you give 7 a go? For 7A, the answer is 8 and 85. And for 7B, the answer is 19. And again, when I went through this, a survey was conducted to determine a student's favorite breeds of dogs, and each student to pick one breed. It would have been nice if I took the time to total these up. So 85 different students were asked their favorite breed of dog, and these were the lists, and these are the selections. And again, these are completely made up. I can't imagine I took the time to survey 85 students, so I just made up some numbers. They have nothing probably to do with reality. All right, so that's kind of one of the three types of probability, the one that's testworthy. The subjective probability, the probability that I think it's going to rain today, or the probability that I think the Suns are going to win the championship, won't be on the test. Empirical probability, this is based on data that's been collected. And it's probably not the most important of the types of probabilities. The most important probability is going to be what we do last, and that's kind of going to be the focus of most of the chapter. Theoretical probability is based on mathematical theories and formulas. And for instance, I can say, what's the probability if I flip a coin that it comes up ahead? And you might say 50% or 1 in 2. That's a theoretical probability. You don't have to flip a coin to maybe think or know that the probability of flipping a coin and getting ahead is 50% or 1 in 2. So I can answer probability questions if I can conceptualize what can happen when I do a specific, experiment, we'll call it. And it's kind of the focus of most of the rest of the chapter. So let me just kind of jump into this. Again, we don't need to know the definitions. Subjective probability is just an educated guess. Empirical probability, we're using data collected to answer probability questions. Theoretical probability, we don't actually have to collect data. We can just conceptualize what can happen and answer probability questions. So here's an example of a theoretical probability question. So I have some jar that has 40 white marbles, 60 blue marbles, 50 red marbles, 30 yellow marbles, and 20 green marbles. How many is that? 40, 100, 150, 200. This jar has 200 marbles. So I can maybe answer hypothetical questions about closing my eyes, sticking my hand in that jar, and pulling out a marble, and I can answer questions on the probability of getting a certain color without actually going through and pulling a marble from that jar. So find the theoretical. So I'm going to pick one marble from this jar. Find the theoretical probability that the marble is red. Simple thing to do. To do probabilities, I need to form a fraction, whether it's theoretical or empirical. And the denominator is the number of things that can happen. The numerator is the number of outcomes or number of tests that would have the right test. So for this particular goal, my goal is to pull a red marble out, and I'm going to answer this question by forming a fraction. In the numerator of my fraction is going to be the number of red marbles that are in the jar, because my goal is to pull a red one out. And the denominator is going to be the number of marbles, because I want to pull a red one out, but I could pull any of the marbles out. The numerator is going to be 50 because there's 50 red marbles in the jar. So when I reach my hand in, I can pull out any one of the 50 red marbles, and that would be a good thing. Unfortunately, there are a lot of marbles that aren't red, and I might get some of the bad marbles. So the probability of getting a red marble is the 50 marbles that are red out of the 200 marbles. Let me reduce this fraction. To reduce 50 out of 200 without my calculator, I can lump all these zeros and get 5 and 20. And then I can reduce that by 5. 5 divided by 5 is 1. 20 divided by 5 is 4. So down here I said the probability of getting a red marble from this theoretical jar is 1 in 4. Let's do another one. Find the theoretical probability that you get a red or a green marble. So when I go to do this problem, I am going to form a fraction, and in the denominator, because this jar has 200 marbles, it's going to be 200, because the denominator is the number of events that can happen, and I can get any one of the 200 marbles. I'm going to call this a success if I get a red or a green. And in order to figure out what the numerator is, I need to find the number of marbles that have the desired characteristic. Well, there are 50 red marbles and 20 green marbles. So in this jar of 200 marbles, there's 70 marbles that classify as red or green. So I'm going to say the probability is 70 in 200 that I get a red or a green marble. I'm going to lump out a 0, and for my probability, I wrote 7 in 20 for my answer. For this particular problem, the probability of getting a red or a green marble would be 7 in 20. Last one, I guess. This is a awkwardly asked question, but it's okay. Find the theoretical probability that I pull out one marble, as I'm pulling one marble from this jar, that marble is both at the same time red and green. Well, there is no marble that's red or green is okay, but there's no marble that's both red and green. In the numerator of this fraction, I have to put 0 because there's no one marble that's both red and green. When it said red or green, it counts all the red ones in addition to all the green ones, but in this case I need one marble that's both red and green. There's 0 marbles that are both simultaneously red and green. There's ones that are separately red and separately green. The numerator is going to be the marbles, any marbles of these 200 that are both red and green, which is 0 of them. The denominator is the total number of marbles in the jar, which is 200. When I reduce this fraction, I get 0. This is an impossible event. I can't get a marble that's both red and green because there's no like striped red and green marbles in this particular jar. So it's impossible for me to get a marble that's simultaneously red and green. It means it's impossible. The probability is 0%. I don't think I need to say that. I'm debating right now. I should pause the video while I debate about. So you might be able to jump a few pages until I start doing this example and understand things as well as if you watch me do the next few pages of explanations. The next few pages of explanations have a bunch of definitions, and I'm not sure how much my going through the definitions is going to help or hurt you do the problems. I kind of feel like it might almost hurt you, but then I don't know how to do the problems without doing these next few pages. So if you can skip to the this page and understand my problems without watching these next few minutes of definitions, give it a try. It might be completely doable. If you look at this problem and it gets confusing, then watch what I'm about to do right now and rewind. So I even wrote to myself when I wrote this a few years ago, there are a handful of terms that we should be familiar with for the next group of problems. You certainly can solve the problems without knowing each definition. I almost feel like this page of definitions is a bit much at this point in our discussion about probability. You should make an effort to understand the terms, but I won't ask the definitions on a test. First definition, a probability experiment is a controlled operation that yields a measurable set of results. I promise, if you took this sheet away and asked me to define a probability experiment, I probably couldn't do it. It took me probably of searching something on the internet to get that definition. So here's an example of this definition. A probability experiment. A dice is rolled one time and the number on the top of the dice is recorded. This is a probability experiment because it can be performed in a controlled fashion and the results are measurable. The results are just looking at the number that comes up on the top of the dice. Outcomes are the possible results of a probability of experiment. This experiment is rolling a six-sided dice and recording the number that shows up top. The possible outcomes for this experiment, I can get any number between 1 and 6. Each time this experiment is performed is called a trial. In this case, each time a six-sided dice is rolled, I look at the number that's face up. That's a trial in this experiment of rolling a six-sided dice, this probability experiment of rolling a six-sided dice. Of course, I know the possible outcomes without actually rolling a dice, or can know the possible outcomes because I can look at the dice and know what could come up. Now, it's not the case that every dice is a fair dice. You can weight a dice so one number comes up more frequently than another. We're not going to worry about dice that aren't fair in this particular chapter. So the outcomes for this experiment, the possible outcomes when you roll a dice that's six-sided and record the number that is coming on top, are you can roll any number between the numbers 1 through 6. If I list all the possible outcomes for this experiment, that's what a sample space is called. This is one of the few words that we'll use a lot in this chapter. The sample space is a list of all possible outcomes for some probability experiment. And the probability experiment that we're going to beat on for a little bit is just the simple one of rolling a six-sided dice and recording the number that shows face up. The sample space is a listing of all the possible outcomes. It's usually The sample space is usually defined as a set. It's usually given a capital letter name, and it's written usually in roster form. The sample space for rolling a six-sided dice and recording the number that shows face up can be defined as S stands for sample space, and then I'm going to write the set in roster form. Roster form just involves listing all the possible outcomes and putting them in set braces. So this would be the sample space for rolling a six-sided dice and recording the number that appears on the top. An event is a subset of the sample space. So here's an event. I'll say O is the event that contains the numbers 1, 3, and 5. O is a subset of S, and I gave the set the name O because I thought O means odds. I might say E is an event, and I might say E is the numbers 2, 4, and 6, which means even for E. I might make an event P, 2, 3, and 5, and P meaning prime, and 1 is not a prime number. To be a prime number, one's defined as not a prime number. So an event is any subset of a sample space. I just made 3 subsets of the set S that were special subsets. Subsets containing odd numbers, subsets containing even numbers, subsets containing prime numbers. I can make a subset and call it the letter A and make it 1, 2, 3, 4. That would be an event. So all of these are events. They're subsets of the sample space. The first 3 are kind of special subsets. I formed the sets in such a way that I could talk about the elements and they made sense. O was the odd elements in the set. E was the even numbers. P was the primes. A was just some random subset. So an event is a subset. And there are 2 types of events: simple events and compound events. These, they're events, but they're compound events. They're compound events because they contain more than one element. A simple event contains one element. It's a subset, but it only contains one element from the sample space. Whereas a compound event contains more than one element. So these were 4 compound events. I can make another set like B. B is the set, let's say, that has the number 5. This would be considered a simple event. So an event is a subset of the sample space. A sample space is a listing of all the things that can happen. When I roll a 6-sided dice, the sample space is going to be a set. The sample space is going to be the set containing the numbers 1 through 6. Any subset of the sample space is called an event. If the event has more than one element in it, it's a compound event. If the event only has one element in it, it's a simple event. I'm going to skip over some pages here because I don't think they're that important. We're going to need to use sample spaces and events to compute probabilities. So here, if I had my sample space that I constructed, that's a sample space that's possible from rolling a 6-sided dice, assuming that this is a fair dice and it's equally likely that I get any of the 6 numbers. To find the probability of an event, it's going to be formed by making a fraction. The numerator is going to be the number of elements that make up that event. And the denominator is going to be the number of elements in the sample space. This is way more complicated than it really is. So trying to define probability using proper definitions really does kind of muddy up the scenario. But let me try to do this with one of the simple events that I talked about just a minute ago. So here's our same experiment. A 6-sided dice is rolled and the number that is face up is recorded. Let O be the compound event that the number on the dice is odd. Find the P of O. This right here means find the probability that event O occurs. Well, in order to answer the question, I need to know 2 things. I need to know 2 numbers, essentially. The number for the numerator and the number for the denominator. The number that goes in the numerator are the number of elements that make up this subset. Well, the set that we're taking the subset from is the sample space. So when I roll a 6-sided dice, there are 6 different numbers that could come up. that's going to be the number of elements in the sample space. When I go to find the probability that I roll an odd number, the 6 elements in the set is going to be the denominator, the number for the denominator. The number that goes in the numerator needs to be the number of elements in set O. So I need to know what set O is. And set O is the compound event that the number on the dice is odd. The elements of set O are the numbers 1, 3, and 5. To find the probability of event O, I form a fraction. And in the numerator, it's the number of elements that make up that event. The event is rolling an odd number. The number of elements that make up that event are those 3 numbers. And then the denominator is the number of elements in the sample space. There are 6 elements in the sample space because I could have rolled one of any 6 numbers. So the probability that I roll an odd number, or the probability that event O happens, is 3 and 6, and that reduces to 1 and 2. Let me do another example, a more complicated example. Let I be the event that the number on the dice is greater than 7. Well, I know if I'm rolling a 6-sided dice, the sample space, the numbers that can come up, are the numbers 1, 2, 3, 4, 5, and 6. I is the event that a number greater than 7 is rolled. The first thing I want to do if I want to find the probability of I happening is create the sample space and create the set I that's defined. The sample space is the set that contains the numbers 1 through 6. I is the set that contains any number in the sample space that's bigger than 7. There aren't any elements. It's actually the empty set. There's no number in the sample space that's greater than 7, so I is the empty set. It has 0 elements. To find the probability of I occurring, I'm going to form a fraction. The numerator is going to have the number of elements that make up that event. I look at the event I. The number of elements that make up the event I is 0. The denominator is the number of elements in the sample space. There are 6 elements in the sample space. And that fraction, 0 over 6, reduces to 0. So the probability that event I occurs is 0. It's impossible. And that's the smallest probability. We can't have a probability less than 0. If a probability of an event or a compound event is 0, that means that that event can't happen. I can't roll a 6-sided dice in one time and get a number showing greater than 7. So the answer to part B, the probability is 0. For part C, let W be the event that a number less than 7 is rolled. Find the probability of W. Well, 2 things I need to answer this because I need to form a fraction. The numerator of the fraction is going to be the number of elements that make up event W. The denominator is going to be the number of elements in the sample space. And for this problem, there are 6 elements in the sample space because I can roll any one of 6 numbers. So the P of W means the probability of W happening is going to be a fraction. The numerator needs to be the number of elements in set W, which means I need to create set W. W is the event that a number less than 7 is rolled. I need to take any number in the sample space that's less than 7 and put it in set W, and that's every number. Every number in the set, the sample space, is less than 7. So W contains all the elements of the sample space because I'm wanting to create set W by taking all the elements of the sample space that are less than 7, which is the numbers 1, 2, 3, 4, 5, and 6. Now I'm going to form a fraction. In the numerator, I'm going to put the number of elements that make up set W, which is 6. In the denominator, I'm going to put the number of elements in the sample space, which is 6. I'm going to reduce this and get 1. So the probability of my answer, the probability of W, is equal to 1. If you wanted to, you can make this as a percent, which is 100%. This is an event that has to happen. It's called a sure event. If an event has to happen, its probability is 100%. If an event can't happen, it's an impossible event, its probability is 0. All right, let's do some questions together and see kind of what we can do with them. So, homework's 9 through 22. I'll do 9 with you, and then I'll start doing some evens. So, a TV remote control has numbers for 0 through 9. You're asked to select a key at random. The sample space for this event, I'm going to randomly pick a button between 0 and 9 from this remote control. So the sample space, which is an important part of this, is what can happen when I randomly select a numbered key on this remote control. And there's 9 different numbers that can happen. What is the probability that I pick the channel 6? So I need to create my event. In my event, I'm just going to call E, which is picking the number 6. And I need to create a subset of the sample space that has the number, and only the number 6 in it. This is a simple event. There's one number on this remote control that has the number 6, and it's the only element that goes in this set. The probability of my E, and you don't have to call it E, I just called it E for event. I was going to call it S for 6, but I already have S for sample space. So the probability of an event is the number of elements in the sample space goes in the denominator. The number of elements in that set goes in the numerator. The numerator is going to be 1, the one element in the set that has the number 6. The denominator is going to be 10 because there's the numbers 1 through 9 in addition to 0. The answer to part question A, 9A, is going to be 1 in 10. And I don't have to do probability of E. For part B, I'm going to create an event, and the event is I pick an odd number, and I'm assuming that the elements in here that are odd are the numbers 1, 3, 5, 7, and 9. So if I want to find the probability that I pick an odd number, I'm going to write P of O, meaning the probability I pick an odd number. I'm going to form a fraction. The numerator is going to be the number of elements in this set O that I created. That's the event of getting an odd number, and there's 1, 2, 3, 4, 5 elements in that set. The denominator is going to be the number of elements in the sample space, and there are 10 elements in the sample space. My answer to part B, I would just write the number 1/2, probably because the instructions say write my answer as a reduced fraction. Sometimes I write my answers as percents, but usually when I do probabilities, I do reduced fractions. Okay, C, what is the probability press a key for a number less than 7? I need to make up the set. I'll do L for less than. And let me write the elements in the event that make up the numbers less than 7. I think the numbers 0 through 6 are the numbers that are less than 7. So now I'm going to form my fraction. The probability of this event, L, I can get by making a fraction. The numerator needs to be the number of elements in this set, and there's the numbers 1 through 6 plus 0. There's 7 elements in that set. The sample space has 10 elements. The number of elements in the sample space go in the denominator. The answer to part C, the probability that you press a key for a number less than 7 is 7 in 10. I need to yank out something for these problems here real quickly. Problems 11 through 30 say one card is selected from a deck of cards. Find the probability that the card is, and then write your answer as a reduced fraction. Let me pause my video for a little bit and get something to help us understand a deck of cards. So we're about to do probabilities that involve picking one card from a deck of cards. Here is my sample space. This is a listing of all the possible cards I can pick from. I can pick. And it turns out that there's 52 cards in a deck of cards. There are 4 suits. Their suits are clubs, diamonds, hearts, and spades. There are 13 clubs, 13 diamonds, 13 hearts, and 13 spades. The diamonds and the hearts, if you're not familiar, they're reds. I don't have a red with me today, so I'll highlight these in pink. The diamonds and the hearts are generally red, and the spades and the clubs are generally black. So now I'm going to answer probability questions, and I'm going to answer probability questions by creating fractions, and every one of the fractions is going to have 52 in the denominator. So for my question 12, I'm finding the probability that I go through this deck of cards and I pick a 3. To form a probability, you need to form a fraction. The denominator of the fraction is the number of elements in the sample space, and the sample space here has 52 cards. The numerator is the number of elements in the sample space that have the characteristic that we want, and the characteristic I want is a 3. And for my sample space here, the event that I'm going to create that is picking a 3 is the set that has the 3 of clubs, the 3 of diamonds, the 3 of hearts, and the 3 of spades. I used to draw those shapes, but it's really pretty sad when I do it. So the event that I'm trying to find the probability of is the event of picking a 3. The denominator for this probability is 52 because there's 52 cards in the deck. The numerator is going to be 4 because the event picking a 3 has 4 cards in the sample space that fit that characteristic. So that's 4 and 52. I'm going to reduce that fraction to 1 and 13. My answer for number 12 is going to be 1 and 13. When you go to do number 11, if you do set 11, I think you should also get 1 and 13 for your answer. So eventually, if I write down the set every time that I'm creating for the numerator, it's going to take a ridiculous amount of time, and I'm going to start slowing us down too much if I do that every time. So let me work on 14. 14 says, what's the probability that I pick a spade when I pick one card from a deck of cards? The numerator is the hard one. It's the number of spades in my deck of cards. The denominator is the number of cards possible. So I'm going to form a fraction. In the numerator, it's just going to be the number of spades in my deck of cards. I could form the set of all the cards that are spades and then count the number of cards in that set, or I can just look at my sample space and visualize that set without writing it down. The denominator is going to be the number of cards in the deck. For all of our questions here, the denominator is going to be 52 cards because there's 52 cards in the deck. The numerator needs to be the number of cards that have the characteristic that I'm looking for, essentially. The characteristic that I'm looking for is spades. And if I count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 spades. This probability is going to be 13 and 52. My answer for problem 14, when I reduce that fraction, is going to be 1 and 4. Your problem 13, the fraction you're going to form is going to have 52 in the denominator because the sample space is the 52 cards. The numerator is going to be the number of hearts in that deck of cards, and I have that written down for you already. When you get a final answer for number 13, it should be 1 and 4. Let me go through 15 with you. To do 15, the probability that I get a black card, I'm going to form a fraction. The denominator is going to be the 52 cards that make up the sample space, the 52 cards that I could choose from. The numerator needs to be all the black cards. And for the black cards in a deck of cards, the clubs are black, and there's 13 of them. And the spades are black. There's 13 of them. The numerator of my fraction, when I'm trying to find the probability if I draw one card from a deck of cards, the probability that I get a black card, the numerator needs to be the number of black cards, and that's going to be the 13 spades plus the 13 clubs. Those are the black cards in my deck. The numerator, this is the event of drawing a black card. It's getting a spade or a club. The numerator is going to have 26 in it for the 26 cards in my deck that are black. And now I'm going to reduce this fraction. The answer to problem 15 is going to be 1 and 2. I'll do 18 while you can give 17 a go. When I look at 18, The denominator is going to be 52 because I'm drawing one card from a deck of cards. The number of elements in the sample space goes in the denominator. There's 52 cards. That's the 52 for the denominator. The numerator needs to be the number of cards in my deck that are both at one card at the same time, both a queen and black. And the cards that from my problem 18 that are going to go in the numerator is this card right here, the queen of clubs, because it's a queen and it's a club, so it's black because clubs are black, and the queen of spades because it's both a queen and it's black. So when you're saying one card has to be two different characteristics, I look for the card that has both that characteristics. The two cards are two cards in my deck of cards that are both queens and black simultaneously, the queen of clubs and the queen of spades. The numerator for my fraction is going to be 2, and when I reduce this, my answer for problem 18 is going to be 1 in 26. For 17, when you go to do your problem, I think you should also get 1 in 26. All right, let me work through problem, well, let me do 19 with you because it's trickier. So to do 19, I'm forming a fraction. The probability of getting a card that's both red and black, the denominator is 52 because there's 52 cards I can pull from. When I look through my deck of cards, cards are not red and black. They're either red or black. Here, like there was a card that was both red or black and a queen, so I was able to do the last problem and get a number from my numerator other than 0. In this particular problem, the numerator would only consist of the cards that, if I look at one card that it's at the same time black and red, there's no cards like that. 0 is going to be my numerator. Since there's no card that's both black and red, I have to put a 0 in the numerator. Unlike black and a queen, there were cards that were blacks and queens. The answer to problem 19 is just going to be 0. It's impossible. Oh, let's look at problem, I'll look at 22 while you look at 21. For all these problems, when we go to do the probability, the denominator is going to be 52 because there's 52 elements in my sample space, which are the 52 cards. For 22, I need to find any card that's both a 7 and a spade. There's actually one of those, the 7 of spades. The card that I'm going to count for number 22, I need a card or any card that's both a spade and a 7, and there's one card when I look at it, I can say that card's a 7 and that card's a spade. That's the 7 of spades. My numerator is going to be 1 in 52. When you go to do your problem 21, you need your card to just be a black card and a 7. You're going to count the 7 of spades because that card is black because it's a spade and it's a 7, so it's a 7. And you're going to count the 7 of clubs. It's a 7 because it's a 7. It's black because it's a club. You're going to get for 21 2 in 52, and you can reduce that to 1 in 26. '23 and 24. For my 24, I need to get something that's both a red card and a 4. My denominator is going to be 52 because there's 52 elements in the sample space. My numerator are going to be two different cards. It's going to be the 4 of diamonds and the 4 of hearts. Hearts and diamonds are red, and there are 2 red 4s. So there's 2 cards in my deck that are both red and a 4. So my numerator is going to be 2 in 52. That's going to reduce to 1 in 26. I believe if you do 23 properly that your answer is going to be 1 in 52. This is a tricky question, so I'll do 25 with you so you don't fall into the trap. So I need to count when I go to form my numerator any card that's a queen or a king. That's different than a queen and a king. So when you go to do problem 25, the numerator needs to be the number of cards in a deck of cards that's either a queen or a king. And what you're going to count, you're going to count all the queens because they satisfy the queen part of queen or a king. And you're going to count all the kings because they satisfy the king part of queen or king. The numerator of your fraction for problem 25 is going to be those 8 cards. There's 8 cards in my deck of cards that are either a queen or a king. I'm going to reduce that fraction in number 25, and that reduces to 2 and 13. When we go to do 27 and 28, that's a little bit different. When we go to do either one of these, the denominator is going to be 52 because I'm trying to pick from any one of the 52 cards in the deck. When I go to do 28, I'm looking for one card that I can look at and say it's both at the same time a queen and a jack. If this said queen or jack, I'd put an 8 in the numerator because you can count the queens and the jacks separately. Queen and a jack is looking for one card that has a queen picture and a jack picture on it simultaneously. There aren't any cards that are single cards that are both queens and jacks, so that's a 0. When we go to do 29 and 30, we're counting up anything that's either. Ors are nicer. When I go to do problem 30, I'm going to, in the denominator, make a 52 in my denominator because there's 52 cards in the deck. My numerator for 30 is going to count up all the jacks for the jack part, and then the or part allows me to count up all the kings. There's 4 jacks and 4 kings. Because of the word or, they don't have to be both a jack and a king. They could be a jack or a king. I'm going to get 8 and 52. And 8 and 52, I thought that reduced it to like 2 and 13. So I'm going to write 2 and 13 for my answer. Let me pause the video and do a part 2 just because it's getting kind of long.